And then the following session will be topic 3, which is thermal physics. So, give you an idea of where we're headed. So today we really need to dive into forces and really get a good idea of forces and review and refresh our memory. Some of us have seen forces more recently than others, and so that's what we're going to cover. The first thing is calculate the weight of a body using the expression W equals mg. We should all know how to get the weight of an object. It's the force due to gravity. Gravity is not a force in and of itself. Gravity acting on an object is a force. Okay, so your weight, or what we say Fg or W, is equal to the mass times gravity of an object. I think most of us are pretty familiar with that. Now your mass doesn't change, it doesn't matter where you go. You can go to another planet, your mass is not going to change, because your mass is the amount of matter that makes you up. It's the total amount of the matter inside of you. And that's not going to change. If you go to Mars, Jupiter, the moon, it does not matter where you go. Your matter is your matter. Okay? But because gravity is different on each of these planets, your weight is going to be different on each of these planets. So, in fact, you actually weigh a lot more, 2.5 times what you'd weigh here on planet Earth if you went to Jupiter. Whereas you're 1/6 of your weight if you actually went to the moon. So, I think the moon is a better place for me, personally. That would be kind of nice. There are 5 main types of forces that we deal with in any force problem that we have to identify when we're drawing a free body diagram. And one of those is the weight of the object. Now, all objects are assumed to have weight. There is no real such thing as no weight. When we're talking about going to another planet, or if we're talking about a body or an object, having no weight, it would basically mean that that object really doesn't exist. So an object has to have some form of weight. And so we pretty much will see that. Now, weightlessness means you just weigh less. It doesn't mean you weigh nothing. Somebody said, well, if I go to the moon, I weigh nothing. No, I'm pretty sure you weigh something. You just don't weigh as much as you do here, and that's where the word weightlessness came from. That's why it says weightlessness, because we're weighing less. A normal force. A normal force is the force of a surface acting on an object. It acts exactly perpendicular to that object on the surface. So, here we have let's say a car, and it's on an incline, okay? The normal force is this surface of the incline acting on this car, so it would act this way, acting up, and that would be our normal force, okay? Now, in the same way, what if I'm on a roller coaster, and here I am, whee, I'm upside down. Well, what's acting on it? Well, yeah, we do have weight, of course, but we also have a normal force here because it's touching a surface. The normal force acts perpendicular to it. It's pushing on the object. It's the force of the surface pushing on the object. So this is going to push, and the normal force would be acting this way. So you actually have to look and see where's the surface and which way is it pushing. Bless you. So that's the normal force. The third type of force that we deal with is a frictional force. And we might be somewhat familiar with frictional forces. They're based off of the microscopic particles as they slide past one another on a surface. Now, it takes more to start moving than it does to keep moving, and I think you kind of know it takes a little bit more to get out of bed than it does to keep moving once you're out of the bed. That's just, that's physics. In motion. That's physics. It does take a force to cause a change in motion. So friction, there's several types of friction. There's 4 main types of friction that we do talk about. One of them is viscosity, and we don't use it a lot in physics. It's more frequently and more commonly used in our chemistry classes. But viscosity, the resistance of a fluid to move or flow, is actually a type of resistive force. Okay. Air resistance. Air resistance always acts opposite of any motion, and therefore it is a resistive force. It acts against the motion. And then there's 2 types of friction that we're most commonly known for. That's kinetic and static friction. Kinetic friction is the friction you have to overcome to keep moving. Kinetic friction, keep moving. And then static friction is the friction you have to overcome to start moving. So it's going to take a lot more static friction that I have to overcome to move before I can actually overcome the kinetic to keep moving. And so your static friction is always going to be greater than your kinetic friction. That's just good stuff to know. The fourth force that we talk about is tension. And that's any time you have a string attached. Now, if you're pulling on the string on the opposite side, those forces inside that string are equal but opposite. And, that's where Newton's third law comes in. And that's how that's really applied. So that tension could actually be an applied force if you're the person pulling on the other side of that. So they could be one and the same. And then, of course, an applied force, and that's usually when they're telling you you're pushing or you're pulling on an object. We don't see it as often in a lot of the problems that I've seen most recently with IB. They don't tend to have as many of those. Now, you notice that I didn't include centripetal force.
No.
Because centripetal force is a net force. It's the sum of forces. It's not actually one of our 5 types of forces. It's actually just sum of forces. We call it centripetal because its type of acceleration is unique to it. Centripetal acceleration is v squared over r, and we use that anytime we move in a semicircle or a complete circular path. We'll use that type of acceleration. So when we say centripetal force, we just means that our sum of our forces is equal to mass times that type of acceleration. We don't actually have a centripetal force. There is no centripetal force. It's not one of our 5 forces. It's just a sum of forces. And so, in fact, it gets confusing because people think it's an additional force, but it's not an additional force. It's just the net force like any other net force we would be doing. It just has a special condition. We use centripetal acceleration in it. And that's where that comes from. Now, one of the things that they want us to be able to understand is Newton's 3 laws. Okay? We need to be able to state Newton's 3 laws because they could ask you to state them. So we want to be able to do that. So Newton's first law says basically that an object in motion remains in motion and an object at rest remains at rest unless it's acted upon by a net external force. So that means this chair right here is not going to move unless something acts on this chair. It's going to remain at rest. And this chair, if I push it, will continue in motion until something stops it, like friction, or it hitting something. Another force has to cause it to stop. Otherwise, it would just continue forever. Okay, so an object in motion remains in motion, and an object at rest remains at rest until it's acted upon by a net external force. Force from the outside. Okay? And of course, they can ask you to give an example of where we might see this in real life and in the real world. And I'm sure it's the same at Trinity at lunchtime when we're trying to get off campus for lunch, So you're trying to get off campus for lunch, and you're in the parking lot, and all of a sudden you see your chance to go, and what do? You slam on the gas. And what does your body feel? Right, because the force of that gas is acting on the car. It's not acting on you, it's acting on the car. You're an object at rest. Your body wants to remain at rest. Right? So that thrust that you're feeling backward is because the force acted on the car, not on you. You're trying to remain at rest. Now, obviously, those two catch up because the seat is going to with you, Otherwise, it would be a little awkward. I'm thinking might be a tad bit awkward, you being just kind of left there. So, yeah, that would be strange. And of course, like any good parking lot. Hi, James. Handouts. So like any good parking lot, of course, there's always your fair share of, oops, I almost hit somebody, because they crossed right in front of you, not paying attention. So at that moment, you, like a good driver, because State Farm is not always really there, you slam on the brake, and what do you
Blare
feel?
your horn.
You go, yes, and you have experienced that this morning from what I've heard.
I slid to a stop.
Yes, because there is actually, you actually have to be able to calculate that stopping distance. That's our motion stuff. Or we could do momentum impulse theorem, which we'll learn about a little bit later. So you'll slam on the brake because you don't want to hit somebody, right? And what does your body feel? Instead of the thrust back, now you're feeling the thrust forward. Okay? Because that force of the brake acted upon the car. That was a force on the vehicle, not a force on you. So you're an object and you were technically already in motion, so your body wants to continue in motion. It goes, woo, straight forward. Okay? Now, of course, this is where Newton's third law comes in, because Newton's third law, which is really stated very, I think a lot of people understate Newton's third law. Okay, and I think Newton would be pretty upset about that, because we like to say for every action there's an equal but opposite reaction. But that implies that the forces could cancel each other out. And we know that the forces don't cancel each other out, because if they're equal but opposite, then I'd never freaking be able to move. I wouldn't be able to move if the forces canceled each other out. So we know that they don't. So when you say every action has an equal but opposite reaction, oh no, they're two different objects. And that has to be clear. And that's why he stated the third law the way he did, which is why IV does not like you to say for every action there's an equal but opposite reaction, because that's assuming they're acting on the same object and that those forces would cancel, and we know that's not true. So then you say, well, how would I state Newton's third law so that I truly, completely understand what I'm supposed to say? Well, object A acts on object B acts on object A, equal forces but opposite directions. They're equal in magnitude, but they're opposite in direction. So A on B, B on A. A on B, B on A. So if gravity's acting on a lamp, what's the equal but opposite reaction?
Normal force.
Earth acting back up. If you have a lamp hanging from a wire, it's the same thing too. If a lamp's hanging from a wire, you would think, okay, gravity's acting on the lamp, so the lamp's acting on the wire. That would be the opposite direction, right? What if it's not on a surface? Because, you know, your reaction to, say, normal force is pretty common. So what if it was hanging from a wire? It has a weight. Weight is gravity, right? Pulling you on Earth. Earth acts on, yeah, it's the opposite, and it drives you kind of crazy if you think about it, because you're thinking, wow, the opposite of weight is the Earth acting on the object. Gravity acting down, the Earth acting the opposite. And we miss that a lot in the multiple choice, and that's when they like to ask that question, because that actually is something that, you know, it's not innate to us. Because the first thing I would be thinking is, hey, I have a lamp, guess what's the opposite? It's the normal force, right? That's exactly what I think. Or the tension, if it was a hanging lamp. But since it's gravity acting on it, gravity's pulling you to Earth. So Earth acts on, yep, so odd. And it seems so odd when you answer that question, but that's why it's missed so frequently. It's for that reason, because we don't innately and instinctively think that way. We're thinking about our free body diagrams, and I'm thinking, hey, my weight's down. What's acting the opposite of that in my picture? So I wouldn't have thought to answer it that way. But that's the reason why we have reviews. That's why we're talking about it. It's for that reason. So that's where third law. Now, of course, in my car, how is my third law implied? Well, hey, I just slammed on my brakes, right? So it stopped my car, but my body continues to move forward. So since my body continues to move forward, my seatbelt is going to catch me. It's going to exert an equal force. Seatbelt acts on me. I'm acting on seatbelt, right? Equal forces in magnitude, but opposite in direction. So that's an application of third law. Now, also way understated is Newton's second law. In fact, it's so crazy because the state has simplified it on the tax test to be F equals MA. If it was only that easy, we would not be having this review. Seriously, would we be having a review if it was just F equals MA and we had to plug in 3 little variables? Probably not. So apparently it's a little bit more complex than that. In fact, when Newton first stated his law, it actually wasn't even the net force is equal to mass times acceleration, because that's what people think it is. Net force equals mass times acceleration. Net force meaning the sum of forces. And so a lot of us like to put that down on paper, but that's not really what he said. In fact, he didn't even actually say that A, the acceleration, is proportional to the force, net force, and inversely to the mass. He didn't even say that, which is what people think he said. He didn't even say that. So let's take a look at what he actually was talking about. Your net force is equal to your mass times acceleration. We know it's not just F equals ma. And so then we realized, oh, okay, it's net force. It's the sum of the forces. It's the net force. Okay, I get that. That's fine. I can do that. But then you realize, oh no, Newton actually said that it really was the acceleration is proportional to the net force and inversely to the mass. But in fact, that's not actually what he really said either. You know, in a way it is, but in a way it's not. Because in fact, what is acceleration? A change in our velocity over the change in time, right? That's what acceleration is. So when I plug in that, I get this. And then I realize, oh, okay, well, there's a thing called momentum. And momentum is mass times velocity, and a change in momentum would look like this. So let's talk about what momentum is. If momentum is mass times velocity, a change in momentum would be final momentum minus my initial momentum, right?
Mm-hmm. Over change in time, right?
Not yet.
Okay. Sorry.
Right. So this is mv final minus mv initial, and obviously the mass is probably not going to change in that. So I can pull that mass out, and I have v final minus v initial, which that looks an awful lot like just a change in velocity, right? So change in momentum is mass times a change in velocity. That's what a change in momentum really is. So when I see it like this, I realize, hey, that is a change in my momentum. That's exactly what it is. It's a change in momentum. So really, the net force is my change in my momentum over time. And really, that is what he said. It's the rate of change in momentum. That is what the net force is. He said, in his second law, that the net force is equal to the rate of change of momentum. That's what he was saying. It's equal to the rate of change of momentum. Now, rate of always means over time, and change in momentum, right? But what we don't want to do is we don't want to confuse the net force with what impulse is. Because a lot of people do that. They confuse net force with impulse. Well, we can get impulse. This is impulse. And it's equal to the change in momentum. And what I see a lot of students do is they say that the net force, or that the impulse is equal to the rate of change in momentum. Well, that's not true, is it? Impulse is not equal to the rate of change in momentum. No, net force is equal to the rate of change in momentum. Impulse is equal to, and one of the things that IB asks a lot in definitions is, define impulse. Can we define impulse? Force times change in time. That is impulse. That is impulse. Now, how is that related to momentum? Well, it's equal to the change in momentum. So if I know the change in momentum, I know the impulse. And you say, well, I don't even really know what momentum is, so that doesn't help me. In fact, I don't even think I know what impulse is. And I say, oh, okay. Well, let's talk about what these things are. If you're in a shower, and you get out of the shower, and you're walking around in a towel in the locker room, la 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 la, and you hope that nobody's being an idiot, but people are. I know this. I was in high school once, and you know. You know, if you take a towel and you go like this, you're not going to go, right? You're not going to, and hit them really, really soft. You're going to do it really fast, right? Why would you do it really fast?
Because it hurts more.
This is going to hurt more, right?
A lot more.
Exactly. So when I decrease the time, it increases the force, right? That's an application of our impulse. Right? Airbags. What do airbags do? They increase the amount of time during a collision. Increase the time, decreases the force. That is how we use this on a daily basis. That's where we see it. This is also the reason why you follow through. You don't just go, hey, no, follow through all the way. You don't just wing it. Ooh, that's not going to get very far, right?
Unless you're playing Wii baseball.
Right.
Because you just go like that, or it's
Yeah,
the
well,
throwing
it-
100-mile-per-hour pitch.
Yeah, I could see that. But usually you fall through.
Increase the force.
And that's the reason for it. Okay. So that's where impulse comes in. You say, well, I'm still not really understanding the difference between force, impulse, momentum. And I say, okay, so you get into a collision. Well, you almost had one, so let's just say you did. You get into a collision. Obviously, with the construction, it's so much easier to do. You get into an accident, and the person standing on the side says, wow, that truck sure had a lot of force. And I'm thinking, no. It's a force in an itty-bitty car, and a truck and a car, and they collide, and I'm thinking, no, because I'm pretty sure Newton's third law applies. A on B, B on A, equal forces, opposite directions. Oh, wait. Same amount of force. And you say, well, how is that possible? And I will say, well, okay, we know that the truck has a big mass. And the itty-bitty vehicle has a itty-bitty mass. Well, a really, really big truck isn't able to change its velocity easily. No. So since acceleration is a change in velocity over time, or the rate of change of velocity, we can actually say it doesn't really do much on its acceleration. But the little bitty car,
Sped up
can
really
it change its
quickly.
velocity easily? Absolutely. And so and we can say that this is a proportional type of relationship. For that reason, they're equal. But then you say, well, why is it that the car is obliterated if it got hit by that big truck? That's momentum. Momentum is the mass times the velocity in which they're moving at. Okay? So a really gigantic truck, if he's moving at the same velocity as that little bitty car, and they hit one another, the really big truck has more momentum. They had the same velocity. Big truck has more momentum. Mass times velocity. It's the momentum that does it. And so the person standing out there is really wrong when it comes to physics. In fact, they probably have never taken a physics class in their life because, you know, until recently, it wasn't a requirement to graduate. So now more people are going to become more educated and hopefully not say quite as many stupid things. The fact is, it's so socially acceptable that it's probably never going to be okay. I'm going to be fighting the battle of all these things for the rest of my career. Bless you.
Thank you.
But hopefully that will get better with time. Okay, so your impulse is your force times the change in time. Your momentum is your mass times velocity. And if you're in a collision, your forces are equal in magnitude, but they're opposite in direction between the two objects, and that has to do with Newton's third law. So they can ask you to define impulse, force, times the change in time. They can ask you to define momentum, which is mass times velocity, right? And then, of course, they can ask you, how do you get to the conservation of momentum? The conservation of momentum says that the total momentum, which means the sum of all the momentum, in an isolated system, meaning we have the same objects before and the same objects at the end, is conserved. The total momentum in an isolated system is conserved. So as long as I'm talking about the same objects in the beginning, and I account for all the same objects in the end, it's an isolated system, and it's conserved, which means the sum of the momentums before is equal to the sum of the momentums after. And you say, well, how did we ever get to that idea? Because, you know, this is forces, right? Well, we just linked force and momentum, did we not? Yes, we did. And in fact, that is actually Newton's second law, and third law is how we actually get to the law of conservation of momentum. So let's talk about that. How do we get there? Well, here we say that Newton's second law tells us that the net force is equal to the rate of change of momentum. So I've just linked force and momentum, right? Mm-hmm. Which gives me the impulse momentum theorem. So that's how Newton's second law gets us to that. Newton's second law is going to relate the force and the momentum. And then you say, well, I'm trying to get to the law of conservation of momentum, so that doesn't really help me much. I said, well, you just got force to momentum, so just wait. And Newton's third law says what? Object A acts on object B, and B acts on A, equal forces opposite directions, right? So let's say I have two objects here. We'll call this A and this one B. The force of A acting on B, we'll say, is positive FAB, right? Because it's going in the positive direction. And B acts on A. Let's make sure that this is just as long, right? And it's going to be in the opposite direction plus U, right? So if I have equal forces acting in opposite directions, I can say okay, because Newton's second law, right? Newton's second law related the force to the change of momentum. Okay? So if Newton's second law says basically that the rate of change of the momentum is equal to the force, Newton's third law says that if A acts on B and B acts on A with equal forces in opposite directions, then this is true because the forces are equal but opposite. This is the change of momentum for that, and this is the change of momentum for that. If these two forces act at the exact same time, and those forces are equal but opposite, equal magnitude, so the numerical value is the same, but opposite in direction, so those numbers are the same. If they act in the same amount of time, those are the same. Then that means this must be equal to this. Agreed? That means the change of momentum is equal to that change of momentum. So the change of momentum are equal. They just happen to be opposite direction. So if you actually did this in a lab, you'd actually find that that would be the case. And that's how they get the law of conservation of momentum. Total momentum in an isolated system is conserved. Conserved meaning the same, equal. Absolutely equal. The change in the momentum is equal to the change in momentum. Which means, is there really a change in the momentum from the beginning to the end? No, because it's conserved. Which means if I have positive 12 in the beginning, I should have 12 in the end, right? Whatever I have in the beginning, I should have in the end. That's what law of conservation of. You probably saw it and are more have heard this before, but, matter cannot be created or destroyed in your chemistry class.
It's not the same with energy.
Yeah. You did it, that's why you balanced the chemical equations in those classes, right? Because whatever you had and the reactants you had to have in the products, you can't create it It can't be destroyed, and it's conserved. That's what conservation means. Whatever you have in the beginning, you have to have at the end. Same thing with energy. Whatever total energy I have in the beginning, I have to have at the end, and the same thing is for momentum. Whatever momentum I have going in, I have to have at the end. So those are all the same, right? Yeah. So that's actually how they get to that. That's where that comes from. Now, in addition to that, you can also see a graph. And if it's a graph that is force versus time, whatever the area is underneath the graph is going to represent what? Well, area is y times x, length times width, right? In the case of a triangle, it would be 1/2 our base times height. But it's the area underneath. It's usually our y times our x. So our y value is f, and our x value would be our change in time. What is that? Our change, it's equal to the change in momentum, but it's called impulse. So the area underneath this is representative of impulse, or you could also call it the change in momentum, because we know that impulse is equal to the change in momentum. So if I see it on a graph, I can do that. Now, if they give me some weird shape, which sometimes they have been known to do, they give you some weird shape. I have seen this.
Geometry.
Looks like this. Usually there's little boxes underneath it. If you get the area of the box and multiply by the number of boxes that you count, then you can get the area underneath. That would be the thing to do.
Integration.
Yeah, it's absolutely an integral. Okay? So that's how I would do that. Now, there are 3 main types of collisions you need to be familiar with. 3. Okay? And it is very important that you're familiar with 3 types of collisions. Although they really hit on 2 of them the most. But there's 3 types. There's elastic, inelastic, and perfectly inelastic. Now, this could be also called totally inelastic as well. So perfectly or totally. And in this condition, the objects collide and they stick together and move off together. So they stick together and move off, bless you, together. Okay? Stick together and move off together. And since we're talking about the same objects before and the same objects at the end, momentum is conserved. So we can say that. Okay. Now, elastic and inelastic. They're still talking about the same objects before and the same objects after, so momentum is going to be conserved in all of these. Assuming an isolated system. In an elastic and an inelastic collision, they collide and separate in both. So how the heck am I supposed to know the difference between them? Collide and separate. Collide and separate. So if they both collide and separate and momentum's conserved in both, how do I know the difference between elastic and inelastic? What's the difference? Well, in an elastic collision, they collide, they separate, but it's kind of like having 2 rubber balls bounce off of each other. In an elastic collision, the kinetic energy is also conserved. Kinetic energy is also conserved. Whereas in an inelastic collision, that's not the case. some of the energy is given off. This is more like a real-world collision, where you collide and you get heat, light, and sound. So some energy is given off as heat, light, sound. Now, for sure, we know about the sound. Back when they had metal bumpers, which is not really common now, but when they had metal bumpers, there would be sparks. And then heat, of course, when they had metal bumpers, you could actually touch the bumper at the end, and it was really warm. They've done away with a lot of that. We're now using all kinds of other materials to make our vehicles because it's safety reasons. That makes sense. Of course, they're not quite as durable. You have this like 5-mile-an-hour bumper. You hit something, oh, there goes your bumper. It's going to cost you $500, $600 to replace that thing. So don't hit anything. It's kind of a warning. Don't even tap anything. It's gone. All you have to do is break a bracket. It'll break a bracket. You hit it, it's designed to break a bracket. There goes your entire bumper. You have to replace it. Expensive. But you don't quite get the heat anymore because of the type of insulating material that it is. So we don't quite get as much heat, but the temperature does change slightly because the molecules are moving faster because we transfer kinetic energy. Oh, energies are next session, by the way, on the 5th. So we'll learn more about that. Okay. But those are the 3 types of collisions. So a lot of times what they'll do is they'll ask you, is it elastic or inelastic, or can you even tell, you know, what type of collision it is? And the only way to actually know the difference is to look at the kinetic energy. Otherwise, you have no way of knowing. So if they don't give you enough information to figure out the kinetic energy and whether or not it's conserved or not, then you can't figure out what type of collision it is. Because that's really the only difference between elastic and inelastic. The last one's really easy to tell because they collide and they stick together. That's, you know, that's different. That's what makes it unique. But the first 2, and we will have problems where we'll deal with that. Okay. Now there is a special condition. It's called translational equilibrium, and IB does expect you to not only recognize it but also understand that vocabulary word. It's called translational equilibrium. Translational equilibrium. When you've reached translational equilibrium, it means your net force, or your sum of your forces, is equal to 0. Which means 2 things are possible. You're going at a constant velocity, which means you're not accelerating. Or you could be not moving at all. Right? That would also give you no acceleration. So if you have no acceleration, then obviously your net force would be equal to 0.
Yeah.
What conditions give you no acceleration? Constant velocity, or if it's not moving. That would give you no acceleration, right? Either one of those. So one of the things you have to be very careful about on the IB exam is paying attention to whether or not the object's moving, or if it's moving at a constant velocity. Because in most cases on your IB exam, they're moving at a constant velocity, which means your net force, whether it be horizontally or vertically, they're going to sum to be equal to 0. And that gives you a lot of information and a lot that you can work with. But if you don't pay attention to it, you won't realize it is a constant velocity, and you will forget, and you'll set the net force equal to mass times acceleration. And then you'll be sitting there going, I don't have enough information. And that really sucks when you're sitting there on a force problem and you can't figure it out. We don't want that to happen. So pay careful attention to that, because that is something that tricks you. The other thing in any force problem, as my students learned last year, not all the time is friction neglected. Not all the time. In fact, in a lot of cases, you can't neglect the friction because they want you to solve and find how much friction was present. So you have to be careful about that, because you can't just neglect it all the time. So you need to pay attention for a couple of reasons. You need to pay attention to Is the air resistance or the resistance able to be neglected or not? That's one thing. In any force problem, you should be looking, can I neglect it or not? If I can, great. If I can't, great. I need to know that before I work the problem. Second thing, is it moving or at a constant velocity? Because those are really important things that you have to pay attention to when you're doing the problem. Okay? And then circular motion is also included with our forces. So an object that moves in a circle, okay? There's a couple things they want you to know about an object that moves in a circle or a semicircular path. And I've kind of alluded to a little bit of it because it fits right in with what we're talking about. But when I move an object in a semicircular path around, where is the velocity?
Always
Genial.
So if this is my object here, and my object is moving this way around my circle, it's tangent to it in the direction of the motion. What I see a lot of students do is you're asked to draw the velocity on here, and they go, I'm pretty sure that the velocity is not opposite the direction the object's moving. You just drew it tangent because you're so used to drawing it to the right that you didn't even pay attention. You have to pay attention to the direction it's moving. So if it's moving this way, this would be. Now obviously this means that if an object was on a string and all of a sudden the string broke, it would actually move tangent to that circle. So this is your velocity. It's always tangent to it. Which direction is your acceleration? Towards the middle. So your acceleration is towards the middle. This is the kinematics, drawing the kinematics on there. Now if I was asked to draw the force on there, the force goes in the same direction as the acceleration, which becomes very, very important when I'm doing a circular problem, because my acceleration, if I'm up here, my acceleration is down, which is negative. And if I forget to put the negative sign on that, then I probably screwed up my entire problem. Happens a lot. Or if my object's down here, my acceleration would be towards the center, so it would be in a positive direction. You do have to actually put the positive or negative on the acceleration. So if you have F equals ma, whichever direction it's accelerating, you need to put that positive or negative on there. Bless you.
So that acceleration is negative?
This acceleration would be negative. Now, we don't put the negative on the picture because the arrow is representing the direction, whereas A is representing the magnitude. And so when IB does it, they might have it labeled or have you label it like this, and then you actually have to recognize, hey, look, the arrow is going down. That means it's negative. So my net force is equal to negative mass times acceleration because my acceleration is negative there. And what kind of acceleration is this? Centripetal acceleration. And they give you in the formula thing that it's v squared over r. So then I sum my forces, whatever they may be. I would have to sum them. So what forces would I have on this object if it was up here? Let's look at our 5 forces. Do I have a weight?
Yes.
Yes. And if this is held by a string, and I'm doing a string and rotating it, okay, I don't have a normal force because it's not on a surface, but I would have tension, and the tension would act this way as well, right? If it was a string, a ball on a string. Now, if this was, let's say, a roller coaster, and the cart was here, I'd have a weight, right? Do I have a normal force? Yes, the normal force is the surface acting on the cart. So it would have a normal force. These look an awful lot alike. Now we're assuming frictionless circumstances. You're not probably applying that force to it. Now here I'm applying the force to the string. So that tension technically is my applied force. Technically. No tension on the roller coaster. That's not a string involved. So these are my forces. So if I sum my forces, let's say in this picture, negative T, negative Fg equals negative mv squared over r. And they can ask me to find the tension. And that's typically what they'll ask. It would be the exact same thing here, but instead of tension, it would be the normal force. And they'd probably ask me to find the reaction force of the rail on the car. The force of the rail on the car. That's the way they word that. It's implying the normal force. Because the force of the rail acting on the car is the normal force. So we can see that. And then I get the question sometimes as well, if I'm dealing with something in a circle, what if they don't give me the velocity? How would I work with a problem if they don't give me velocity? What if they gave me radius and the time? Well, you could do that. What is velocity? Distance over time? Displacement over time? Okay, so if we're moving it, it goes around in a circle. What's that path? 2 pi r? You guys agree?
Yeah.
Circle, 2 pi r? Yeah? Okay. If my math serves me correctly on a Saturday. 2 pi r, and t could be the period of time it takes to do one full complete revolution, which is also known as period. And that's equal to v. Now this is v squared, right? Okay, so square it. So I'm going to square everything in it. So that would be 4 pi squared r squared over t squared, and that would be equal to v squared. And what am I going to do? I'm going to plug that in right there, right? So then I get my acceleration is also equal to 4 pi squared r over t squared. And you go, well, what happened to the other r? It got divided out. If I put this 4 pi squared r squared over t squared, and I divide it by r, I get rid of one of those r's, which leaves me that. Now the great thing is that IB gives you this in the data booklet. So they give it to you. But you have to understand it's not something new that they give to you. It's something that technically, it's just by definition of velocity, how they got that. So it's not anything different. That's how they get that. Great, we're taking a 5-minute break and then we're going to start the problems.